Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to electricity and magnetism, and we will take our discussion forward related to application of Gauss law to determine the electric field due to various charge configurations. So in this video we'll be discussing about electric field due to a uniformly charged spherical shell. So we all know the basic application of Gauss law. We have discussed in the previous videos, and the general statement which says that the total electric flux due to a charge configuration, taking into account a closed surface, that is equal to 1 by epsilon 0 times the net charge enclosed by the closed surface, epsilon 0, which is absolute permittivity. Okay, so this is the general statement. Electric flux, which is the number of electric field lines passing through the closed surface, which is equal to the total charge divided by absolute permittivity, or it is also expressed as the closed surface integral of the electric field intensity, that vector, and the area element vector, the surface area element. So in this case we have a spherical shell, and we have a spherical shell of very small thickness, and it is positively charged, uniformly positively charged, with a total charge Q distributed uniformly. It has a radius of capital R, and it has a surface charge density of sigma. Now there are three situations here. The expression of electric field in case of three separate cases. First, we have to determine the electric field outside the shell, okay, which is this case, okay, this case where we consider this is the central point, okay, the center of the spherical shell, which is hollow inside, no charge, only the charge, positive charge, is uniformly distributed on the surface, the circumference. So we have to determine the electric field at a fixed distance small r from the center, and so that we pick a point, this point P, and taking OP as the radius, we draw a circle. In case of this, a spherical Gaussian surface. This becomes the spherical Gaussian surface with radius equals to OP. Okay, we have to determine the electric field at the point P. So we'll apply Gauss law. So here we know that Gauss law states that the total, okay, here Gauss law states that the surface integral of the electric field vector and the area element vector, that is equal to the total charge enclosed by the spherical Gaussian surface divided by absolute permittivity. Here, if we take this point P, the area element vector for the small area, okay, for this small area, that is ds vector, directed radially outwards, normally to the surface, perpendicular to the surface, directed outwards. We know electric field lines are always directed away from the positive charge. So here the electric field line is directed away from the positive charge, also in the same direction as the area element vector. So both E vector and ds vector, the area element vector, they are in the same direction. They are in the same direction. So the angle between them in this case is equal to 0 degree. Also, another important thing, all the points on this spherical Gaussian surface, they are at a fixed distance from the surface, okay, from this point, from the charge distribution, the spherical shell. So, electric field, the magnitude of the electric field, that is constant. The direction will be different, but their magnitude is constant. So, electric field intensity magnitude is constant, and the angle between area element vector and the electric field intensity, that is equal to 0 degree. So, here now taking this, that is the electric flux. So, this is equal to, leave this, that is equal to closed surface integration of E ds cos 0 degree. Electric field is constant, so this becomes E goes outside, closed surface integration of ds. Now the surface area of a sphere, that is equal to E into 4 pi small r square, because here we have to determine the electric field intensity at this point P, which is at a distance r from the center O. So, this is a spherical surface, Gaussian surface of radius r. So, here the total area, surface area of the sphere, this is a three-dimensional thing. So, the surface area, that is equal to E into 4 pi r square. But we know, as per Gauss law, this electric flux is also equal to the net charge enclosed by the surface divided by epsilon 0. So, this is equal to Q by epsilon 0, because the total charge enclosed within this spherical Gaussian surface, that is equal to Q, this much. This much charge is enclosed within this, positive charge is enclosed within this spherical Gaussian surface. So, this becomes Q by epsilon 0. So, if we want to determine the expression of the electric field, that becomes Q by 4 pi epsilon 0 r square. This is the expression of electric field outside the shell at a distance r from center O. Okay, this. Then we have a second case. Okay, we have a second case. For that, what we'll do is, this second case is on the surface, of the spherical shell. So, in this case, on the surface means just on the surface. Let me use a different ink. Okay, here, just on the surface here, like this. So, we will draw a spherical Gaussian surface, this dotted surface. This becomes the Gaussian surface, because it is, we have to determine the electric field intensity on the surface. Okay. So, here also same thing, if we take an area element vector here, the area element vector will be radially outwards, normally perpendicularly away from the surface, and also the electric field lines, they are also directed in the same direction. So, the angle between E vector and ds vector, that angle also here, it is 0 degree. Again, through the application of Gauss law and applying certain equations here, electric flux, that is equal to closed surface integration of E vector dot ds vector, which is equal to closed surface integration E ds cos 0 degree. Also here, all the points on the surface are at fixed distance capital R from the point. So, they are on the surface, so the electric field intensity will be the same, constant. Okay. So, here it will be equal to E will go outside as it is constant. This will be ds. Here the area of the Gaussian surface is equal to 4 pi capital R square, which is the radius of the spherical shell. This is the electric flux expression. Now we also know that that is equal to, as per Gauss law, is the net charge enclosed by the surface, which is Q, same as the previous one, by epsilon 0 absolute permittivity. So in this case, electric field on the surface, that is equal to Q by 4 pi epsilon 0 capital R square. Simply same as the previous one, just here we replaced small r with capital R. Everything else is the same. Okay, here it is Q by 4 pi epsilon 0 small r square. Here simply we replaced small r with capital R. This is on the surface. On the surface of the shell. Okay, then we have a third case, which is the electric field inside the shell. Okay, inside. So in this case we have considered a point P which is inside the shell. Okay, it is inside the shell at a distance small r from the center O. Okay, this point is located inside the shell. Okay, at a distance r small r from the center O. This is as usual the radius of the spherical shell. So here in this case I have already mentioned that this is a hollow thing, this spherical shell. The charge is only present on the surface of the spherical shell and it has a negligible thickness. Okay, negligible thickness. So we have chosen not to consider it to avoid unnecessary complication. Okay, very small thickness of the spherical shell is there. Okay, so we have chosen not to consider it. So the charge is only present on the surface, not inside. Charge is not present inside, it is not present, there is no charge here. So only on the surface. So for this Gaussian surface, which we have chosen OP as the radius and we have drawn a Gaussian surface, as there is no charge present inside the shell, only on the surface, so the charge enclosed by the Gaussian surface, that is equal to 0. Okay, the charge enclosed by the Gaussian surface, that is equal to 0. As the charge enclosed by the Gaussian surface is equal to 0, so this electric flux E closed surface integration of EDS vector is equal to Q net by epsilon 0. As this becomes 0, this Q net charge enclosed is 0, so this electric field inside the shell, that is also equal to 0. Okay, that is equal to 0. So here if we try to draw a graph here. Okay, if we try to draw a graph, so here we have x-axis and y-axis. In the x-axis we have small r, which is distance from the center O, and on the y-axis we have the electric field. So as you can see, for outside the shell, that is small r is greater than capital R. Let's say the capital R is somewhere here. Okay, the capital R is somewhere here. This is the point. So when R is greater than R, small r is greater than capital R, electric field intensity is equal to Q by 4 pi epsilon 0 R square. So electric field intensity is inversely proportional to square of the distance from the center O. So from this point r greater than r, the electric field intensity, it decreases parabolically, okay, like this. And at this point where r is equal to r, it is maximum, it is maximum. And for r lesser than r, it is 0, it is 0. So here there is parabolic decrease, here it is maximum, here it is 0, okay. The behavior of E versus R graph, okay. So this is the discussion related to electric field intensity due to a uniformly charged spherical shell. Another interesting thing here, for on the surface of the shell, okay, on the surface of the shell, electric field intensity is equal to Q by 4 pi epsilon 0 capital R square. Okay, now we know that the surface charge density is equal to sigma for the spherical shell. So for on the surface of the shell, E is equal to Q by 4 pi epsilon 0 capital R square. Now we know surface charge density is total charge, which is Q in this case, divided by the surface area, the entire surface area of the spherical shell. So that becomes 4 pi R square, okay, 4 pi R square. So now Q here is equal to 4 pi R square sigma. So if we substitute here, it will become 4 pi capital R square sigma by 4 pi R square epsilon 0. So this much gets cancelled, so we have sigma by epsilon 0. This is electric field on the surface. So another expression for the same thing. On the surface, this is the electric field due to a spherical shell. Okay, this is the thing. So you imagine that this is a sphere, okay, the spherical shell is a sphere like this, a three-dimensional object, but it has a certain thickness, okay. It is not solid, it is hollow. This much portion is vacant, it's empty, there is nothing, there is no charge, there is no nothing, only this much portion, okay. Let me use a different ink. Only this much portion contributes to the charge configuration, the electric field, and we have considered a very small thickness and we have not included it here, okay. So this is the thing. So we have calculated the electric field intensity both inside the shell, outside and on the surface, okay. So this is outside the shell, this is on the shell, okay, on the shell, surface of the shell, and this is inside the shell, which is 0. Same thing, same derivation, same calculation, everything. So here let us try to understand this from a 3D perspective. So here the situation is that we have a spherical shell here, okay, this, and if we cut it in half, let's say from the middle, we cut it in half like this, then we will have this thing, okay, we will have this. So if we rotate it, it will be like this, okay, this. If we cut it in half, we will have this. So only this much portion is there which contributes to the electric field, okay, because of the charge, this much portion. This much portion. Remaining is blank, it's hollow, okay. This much portion contributes to the charge. The charge is present only in this much portion, this much thickness, and it is very negligible. This is the whole thing, but if we try to show you how this situation is, we will have this. So first we have the first situation, we have to determine the electric field at a point which is outside the shell, okay, from this to this point, okay. Then we have to determine the electric field, let's say this is P1, another point P2 which is on the surface of the shell, okay. This is the radius capital R, and as this thickness is considered very negligible, this thickness is very small, so we are neglecting it, okay. Outside the surface, outside the shell, on the shell, and then at a point, let's say here P3 which is inside the shell, okay. These are the three situations, okay. These are the three situations, like this and then like this. We will draw Gaussian surfaces with taking that much, this from the center, OP1, OP2 and OP3 as the radius. We will draw spherical Gaussian surfaces. So this is the situation, okay. Imagine it like this.